Alright, so you should have watched the transition to algebra video, and now we're actually going to start talking a little bit about algebra. Keep in mind as we go through this, it's very difficult to do a thorough look at Algebra 1 and Algebra 2 like I would normally do. There will be some topics left out. Basically, because the course is mainly focused on elementary and middle school math, I'm not going to go too deep into algebra, and I really just want to jog your memory. But if there's some topic in here that we cover that you're like, I just don't remember like how to do slope that well, or that's something I always just could not stand in high school and I just want to forget about it, make sure if it's something that makes you feel uncomfortable or you don't feel very well mastered at, that you get a hold of me and that we work together to make sure you get past that. So I'm more than happy to spend some office hours with you, or maybe even a group of students at one time if we need to take a step back and cover a topic more thoroughly. My main thing is I know that for some of you it's been years since you've seen any algebra, so I want to take you back and kind of jog your memory, give you some problems to try, and hopefully it seems easier now than what it did when you first learned it. So we've already talked about the equal sign, what it means. We did those weighty problems to talk about, having things balanced on both sides of the equation. Remember, we discussed earlier in this course that it's important for us to write things using the reflexive property there, where we can say either 5 equals x or x equals 5, that 3 plus x equals 10, or the other way around. We could write the equation like this so that students don't get the idea that the equals means answer. X equals 5 and 5 equals x, you can write them either way. You have both sides equivalent there. Like terms, when you get to the very basic problems in algebra, you're combining like terms. So this number that we have, say for the 2x right here, the number that's in front of the variable, we call that the coefficient. You can think of it as the number in front of the variable. When you don't see a coefficient in front of that variable there, if there's no 2, 3, or negative number, then we assume the coefficient is 1. It's just like when you're talking about apples. You might say that you have 2 apples or 5 apples. But if you have 1 apple, sometimes you'll just say, I have an apple. But you won't put a 1 in front of it, Or you could say, I have 1 apple. But generally, as far as when we're writing out the variables, we don't put the number in front if you just have one of that variable. So if you have 1x plus another x, you can just add the coefficients in front of them. So it's 1 plus 1. This equals 2x. When you have 2x plus 1x, you have 3x's. When you have 5x minus 3x's, you get 2x's. And here, because x is being multiplied by y, and x is by itself right there, we cannot combine those two. So this one is saying x times y, this is just saying 1 times x. You can't combine them. They're what we call not like terms. So like terms have the same variable raised to the same exponent. So this is the same variable as this, both x's, and they're both raised to the first power. Once again, if it's not raised to anything, we say it's raised to the first. So all of these are raised to the first power, but here it's not the same variables. You got x, y, and then you just have x. Now if we had xy plus xy, then we could say that we have 2xy's. So in that case, if they have the same variables raised to the same exponent, you can combine those. Remember when we discuss exponents, that if we have something like x cubed, what that is written out expanded is it's the same thing as x times x times x. That's what x cubed means. I always tell my students it's whatever that base is written out this many times, whatever the exponent is, and then multiplied. So for something like 5 to the 4th, 5 is the base. Write out 5 4 times, and then multiply them. So then we look at multiplying the same bases with different exponents. When we have that, when it's something like 3 times 3, we can say 3 times 3 is equal to what? 9. Or another way we could say this is it is 3 squared. So remember the exponent here is 1 and 1. This is the same thing as 3 squared, which also equals 9. Over here, 3 squared times 3 cubed. Well, 3 squared is 9, and 3 cubed is 27. And then we're going to do 9 times 27, which should be 243. But how else could we write this? This was using order of operations. I did exponents first, and then I multiplied. We could also say that 3 squared times 3 cubed is 3 to the 5th. And notice if we wrote this out, let's expand it up here. We could write this out 3 squared as 3 times 3, and 3 cubed as 3 times 3 times 3. And that's how I got this 3 to the 5th right here. Just like over here, 3 times 3 is 3 squared. Or if we said, look at this next problem, 3 squared times 3 squared, you could say that's the same thing as 9 times 9, which equals 81. Or you could say, well, 3 squared is 3 times 3, and 3 squared is 3 times 3, and then multiplying all of these, you get 3 to the 4th. So in general, what we're doing here is, see if you can see the pattern, how we can go from 3 squared times 3 squared is 3 to the 4th, 3 to the 1st times 3 to the 1st is 3 squared, and 3 squared times 3 cubed is 3 to the 5th. What do you think we do with these exponents to shorten this up? So I get 1 and 1 is 2, 2 and 2 is 4, and 2 and 3 is 5. Well, we're adding them. That's in general. So when you multiply, they have to have the same base. So in this case, 3 and 3 are the bases. This last one we're looking at right here, x and x are the bases. You take the exponents and you add them. So in general, x to the a times x to the b is x to the a plus b. Now, when we divide them, let's see what happens here. 3 divided by 3 is equal to 1. 3 squared divided by 3 squared will be 1. 3 cubed divided by 3 squared. Well, we could write this out. I'm going to use this space up here. We know that 3 cubed is 27, and 3 squared is 9, and this equals 3. 3 to the 5th divided by 3 squared. Well, 3 to the 5th is the same thing as 3 times 3 times 3 times 3 times 3. 3 squared is the same thing as 3 times 3. Now, before I multiply all this out, we can do some canceling over here. So this 3 will cancel with this one, and this one cancels with this one, and I end up with 3 times 3 times 3, which is the same thing as 3 cubed, or 27. So once again, as we're looking at this, we want to look for a pattern that we can do something with these exponents. How we get from 3 to the 5th divided by 3 squared and get 3 cubed. Or 3 cubed divided by 3 squared and get 3 to the 1st. So notice once again, we could expand this like a fraction like we did right here and make this 3 times 3 times 3 over 3 times 3. And then when we start canceling out things, we just get 3 to the 1st. So if you haven't seen it already, it's a lot like multiplication. You know, multiplication, division are opposites. For multiplication, we added the exponents. For division, we're going to subtract them. 5 minus 2 is 3. 3 minus 2 is 1. What's 2 minus 2? 2 minus 2 is 0. So you get 3 to the 0, which equals 1. Here it's to the 1st and to the 1st. 1 minus 1 is 0. So 3 to the 0 still equals 1 right there. Go ahead and try out this one. What do you think x to the 7th divided by x to the 3rd is? For this one, since they're the same bases, we're going to subtract the exponents. So we get x to the 4th. On this one, x to the 5th divided by x cubed times y squared. So let's look at how we would work that one out. If we looked at it as a fraction, so if we had this as x to the 5th over x cubed times y squared, we can cancel out 3 x's with 3 of the x's up top. You know, if you were to expand it, it would look like this. And so looking at it like this, we could cancel this one, and then these two. And you end up with x squared over y squared. You could also look at it, some people have a hard time seeing it like that at first, or believing maybe, because you say, well, these are not like terms, you get the y. Remember, we have to have like terms when we're adding or subtracting. Multiplying and dividing is a little bit different in the rules. So we could split this up into two fractions. We can make it x to the 5th over x cubed times 1 over y squared. Notice if we multiply these fractions using the rules we talked about with multiplying fractions, you just multiply straight across. You'd get x to the 5th and then x cubed y squared. So looking at it like this, now we can divide out that fraction and get x squared up top again. So either way, we're going to follow the same rules we did with dividing over there on the left side. We're going to say we've got an x to the 5th up top and an x cubed in the bottom. So 5 minus 3 is 2. So our answer here is we get x squared divided by y squared. For this one, we can look at it as a fraction as well. You get xyz cubed over x squared y z. So for this one, I'm going to say, look at each variable and divide them out. Y divided by y will just cancel out because y divided by y is just going to give you 1. That's assuming that x, y, and z are not equal to 0. Z cubed divided by z, well, this z will cancel out one of these z's, and you get z squared. And then x over x squared, the x's will cancel, and you just get 1x in the bottom. If it helps you, write this out, expand it. So I'm going to write it out, expand it. Down below, we have x times y times 3 z's here. By 3 z's, it's z, z, z. And then 2 x's, a y, and a z on the bottom. And now this becomes a little bit easier to see why this works out the way it does. This x and this x will equal 1 when you divide them. Same thing with these two y's. And you've got 1z canceling out this z right here. So it gives you just an x on the bottom and z squared up top. So that's your final answer there for this one right here. So in general, let's move this over so we can see it a little bit better. Whoops. Does not want to move for me. There we go. In general, when we have x to the a divided by x to the b, you're going to say that's equal to x to the a minus b. Now, actually, before we move on to distributive property, I do want to say one thing with these negative exponents, what they do. If I have something like x to the negative 3, we can rewrite this as 1 over x cubed. So if you make it a fraction, if the exponent is negative, it drops to the denominator, the base and the exponent with it. If it's already in the denominator, like if I had 1 over y to the negative 4, then this whole thing moves to the numerator. So you get y to the 4th right there. So that's your rule with negative exponents. If it's in the numerator, just drop it down below to the denominator. And if it's in the denominator, it moves up to the numerator. All right, so for the distributive property, I think we may have discussed this earlier this semester, but I just want to remind you of that. Remember, with distributive property, you've got usually a number times a binomial, but you could have it times a trinomial or just any polynomial, really. That just means that each term inside the parentheses here gets multiplied by that number. So I always tell my algebra students to draw swoopties. That's not the actual math term, but they love that term for some reason. So you draw your two swoopties so you remember to multiply it by both of those terms. So 3 times x gives you 3x, and 3 times 1 gives you 3. The distributive property works with subtraction as well when you got a subtraction symbol in there. And the number doesn't have to be in front of the parentheses. It could be on the back side over here, and you can distribute it this way as well because multiplication is commutative. It doesn't matter the order that you multiply things. So if I distribute this negative 3, I get negative 12, and then negative 3 times negative x gives you positive 3x right there. We can also multiply two binomials. Now, you might have heard the trick foiling. Foiling works like, it's just an acronym meaning first, outer, and last. So your first two terms, you multiply those together, you get x squared on this one. And then you multiply the outer, so x times 3 gives you 3x. And then the inner terms, so 2 times x gives you 2x. And then the last terms, so 2 times 3 gives you 6. Then you combine your like terms. You've got a 3x and a 2x, and those combined give you 5x. And that's your two binomials there being multiplied using the foiling method. Now, I've got some students that just absolutely can't stand the FOIL method. It just bothers them, but they're good with the distributive property. The FOIL method is just the distributive property done twice. So you could look at, let's look at this next example right here. Just take the y and distribute it to the next binomial there. So y times x and y times 9. Draw your swoopties. Y times x is yx. Y times 9 is 9y. And then, that's doing the distributive property once. Do it again with the -5 this time. So draw your swoopties. -5 times x is -5x. -5 times 9 is -45. And then these four terms right here, just look and see if you can combine any of them. And this is yx. There are no other yx terms. That's just y. That's just x. And that's just a constant. So there are no terms I can combine here. So my final answer would be yx plus 9y minus 5x minus 45. All right, we can also use algebra tiles to multiply two binomials. So in your resources this week, I've included a link to the National Council of Teacher Mathematics. They have some algebra tiles that you can use there. There's probably other ones online. It's just the first one I came to, and it seemed to work just fine. So go to that link and try out algebra tiles with these as I go through them with you. So here I am on their site, and they actually have this set up so they give you a problem. I'm in the expand section right here, and you've got to show the model right here. So this is saying 5 times 2x. So if you look on your right, you've got these little square tiles for just your constant numbers, and then the x tiles right here. So I'm going to put 5 going across the top. So you just click on them and drag them, and then I'm going to put 2 x's going across the left side right here. There's 1x, and then there's another one. And then we need to show what this works out to be. So this is 1 times x, which is just an x. Oops, let's get in there vertically. Let me do it. Let's try spinning it here. There we go. Actually, it wasn't letting me continue because I forgot to check. So you've got to kind of do the problem they set up for you. So I've got 5 times 2 x's now. Now I can drag in the x's now that they verified that my setup was correct. So I'm going to drag these in, one for each yellow one, because this is 1 times this x gives you this x. And so dragging it all the way across, this answer right here would represent 5 times just 1x. But now I've got to do it for the bottom row, because you've got an x down there you're multiplying it by. And so now all these match up, and I can count. This right here is my answer. 5 times 2x should give me 10 x's, and if I count all these x's up in the middle, I do get 10x. So check it, and there you go. Oh, and they want me to, that's why they're giving me that issue. They want me to type it in and check it. There we go. Look at that, I got it right. Just because it is set up so that you've got to follow along with their problems. This might be a good resource if you're wanting to assign some problems using these. There's another site. Actually, there's probably plenty of sites that allow you to use algebra tiles. This is another one right here. This is the one I'm going to use for our tiles today. So going back to our problem, we want to represent 3x plus 2 times x plus 1. So I'm going to drag out 3 x's. So there's 1, 2, 3. And we want to add 2 to it because we got 3 x's plus 2. And the other part, x plus 1. So I'm going to move an x plus 1 out. Now the interesting thing about this is I want this one to be horizontal, so I just double click on it and it makes it horizontal. So if you wanted it to be negative, you can just click on it once and it will make it negative if you need that. But for us, we want it to be positive. We're going to do x plus 1 here. And so now we can go through and multiply these two. So let's just check and make sure I got the problem copied right. 3x plus 2 times x plus 1. 3x's plus 2 times x plus 1. So x times x, that answer there is going to give me x squared. And then we've got x times x again, which gives me another x squared. X times x one more time gives me x squared there. And then 1 times x is going to give me x. Let's spin that. Then another x. Over here we have 1 times x, which gives me x. All the way down several times. And then you've got 1 times 1, which gives me 1. And 1 times 1 again, which gives me 1. So I don't see where I can put a bar in. There might be somewhere on this page, but I haven't worked with this one enough to show you. But keep in mind your answer is what's in here. This is your 3x plus 2. This is your x plus 1. And so we go through and count these. We have 1, 2, 3x squared. So if I'm writing down my answer, I'm going to say I've got 3x squareds. We've got 1, 2, 3, 4, 5 x's. So plus 5x. And then we had, I believe it was 2 1s there, 2 units. 1, 2 right there. And so working with those is a great way to represent something that's very abstract with something tactile that the students can manipulate and learn how to multiply binomials. If we want to do this using the FOIL method, you would say 3x times x gives me 3x squared. 3x times 1 gives me 3x. 2 times x gives me 2x. And then 2 times 1 gives me 2. And so in the middle, these two terms would combine, and you'd get 5x plus 2 and a 3x squared right there, which is the same answer we had up here. But like I said, it's always great to show multiple ways you can get these answers so you can reach many different students. All right, next question I want to go over with, we talked about this before, but we said anything raised to the 0 is 1, and anything raised to the first power is that number. So the question is, why is that the case? So going back to our rules with exponents, if I had something like 5 to the 7th divided by 5 squared, that would be 5 to the 5th. Well, what if I had 5 squared divided by 5 squared? Well, that's the same thing as 25 over 25, which equals 1. What if I had 5 cubed divided by 5 cubed? Well, that equals 125 over 125, which equals 1. What if I had 5 to the 6th divided by 5 to the 6th? Well, that equals 5 written out 6 times and multiplied, and over 5 written out 6 times and multiplied. And when you divide them out, they're going to cancel just like this, and it's going to equal 1. So in all of these, notice what's happening. 2 minus 2, this is the same thing as 5 to the 0, which equals 1. 3 to the 3, or sorry, 5 to the 3rd, 5 to the 3rd. When you subtract those, you get 5 to the 0, which equals 1. 6 minus 6 is going to give you 5 to the 0, which equals 1. So every time there, I don't like to use the term canceling because I feel like that's overused and the whole concept is lost sometimes when you use the word canceling. But the thing is, you got the same thing over the same thing. That's why when you subtract those exponents, you get something raised to the 0. And the same thing over the same thing is going to give you 1 every time, so long as the denominator is not 0 itself. So that's why anything raised to the 0 power is equal to 1. Now, why is something raised to the first power just equal to that number itself? Well, let's look at this first example I gave, 5 to the 7th being divided by 5 squared. And let's change this 5 squared to a 6. So if I change it to a 6 and I expand this, I get this. So this is 5 to the 7th written out. This is over 5 to the 6th written out. And so each 5 will cancel or divide out to be 1 until you get to this last one right here, which is just 5 over 1, which equals 5. So you could also say that is 5 to the 1st, which is just 5. And so for similar reasons why 5 to the 0 is 1, we can say 5 to the 1st is 5. All right, now we're going to take it back and look at radicals here. So this radical, the way we solve it is to factor out the number underneath the radical, known as the radicand. So if I factor it out, I get 6 times 6. And so if there's nothing written right here in this corner, we assume it's 2, and this radical is representing a square root. So we want to know what square gives you 36. So in this case, it's going to equal 6. Because 6 times 6 is 36, the square root of 36 is 6. Now, keep in mind that you could also say it's equal to negative 6. And the reason why is negative 6 squared is equal to positive 36. But in general, in this course and the other course I teach, pre-calc, if I don't tell you by putting a negative in front, I'm wanting the positive root. So in this case, it had no negative in front, so I just want the positive root of 36, which is 6. Sometimes we will want both the positive and the negative root. And in that case, we'll put a positive and a negative in front, sometimes read as plus or minus. We're meaning we want the positive and the negative root of that answer. Let's try another one, or a few more here. So for the square root of 50, the square root of 50 is not going to be a whole number. We have 50 there, which is not a perfect square, but go ahead and factor it as much as you can. So you get 2 times 25. And 25 breaks up into 5 times 5. Now, this is like the short way that I write it out. It's the way I was taught to do it, but really it's kind of a lazier way of doing things. What we should technically be doing is saying that the square root of 50 is the same thing as the square root of 2 times the square root of 25. And the square root of 25 is the same thing as the square root of 5 times the square root of 5. And now when we look at this, this right here should say something to us. When we say, what is the square root of 5 times the square root of 5? You say, well, that's the square root of 25. What's the square root of 25? The positive root, that is. It's 5. So this mess that I've circled is equal to 5. But we still have this square root of 2 right here, so it gets written right here. So we can rewrite the square root of 50 as 5 times the square root of 2. That's what we call simplifying the radical. Try it with this one right here, the square root of 40. So with the square root of 40, we can break that up into the square root of 5 times the square root of 8. Square root of 5, 5 is a prime number, so we can't go any further with that. But square root of 8 can become square root of 4 times the square root of 2. And the square root of 4 breaks up into root 2 times root 2. And so what we're looking for when we're doing the square root is pairs that match up. So I've got root 2 times root 2. That's going to equal the square root of 4. We know the square root of 4 is 2. What is left over? Well, you still have square root of 2 right here and square root of 5 right there. So whatever's left over, you multiply those back together. Square root of 2 times the square root of 5 is the square root of 10. And that is the square root of 40 simplified. So for this one, you've got square root of 5 times the square root of 12. You could say, well, that's the square root of 60 and simplify it from there. So that just becomes, well, we could go backwards and say square root of 5 times the square root of 12, which is square root of 6 times square root of 2, which is square root of 3 times square root of 2. We're really just coming up with the prime factorization here and then looking for pairs. Here's a pair. So root 2 times root 2 is just 2. And then this is my leftover, square root of 3, square root of 5, which is square root of 15. On this one, I believe my radical got lost right here, so I'll draw one in. I want the fourth root of 16. So basically, I want to know what times itself 4 times over gives you 16. So on the others, we were looking at just a square root. This one, I want the fourth root. So I'm going to do the same thing. I'm going to factor it, and instead of looking for pairs, I'm looking for groups of 4. So this 16 will break up into 4 times 4. And then 4 will break up into 2 times 2 and 2 times 2. And remember, these are all technically root 4, but we kind of it gets messy trying to write all those in there. So typically we just write out the prime factorization and then look for groups of 4. So I've got one group of 4 right there. So pull out just 1, 2. So the fourth root of 16 is 2. For the third root of 8, or another way to say that, the cubic root of 8, I'm going to factor it. That factors into 4 times 2. And then 4 factors into 2 times 2. I'm looking for groups of 3. So look right there. I've got a group of 3. The answer here is also 2. This one says the third root of a negative 64. For this class, we can't take the negative square root of something or the square root of a negative number because we're talking about real numbers. But we can take the third root. So looking at this, let's just factor it out and see if it makes sense. If I factor a negative 64, that breaks up into negative 8 times 8. And then 8 will break up into 4 times 2. Then you have 2 times 2. And then right here we have negative 2 times 4, and then a 2 times 2. And so looking at this, I'm looking for groups of 3. So I've got one group of 3 right here. And I've got another group, see, we could take this 2 and make it negative 1 times 2, another group of 2 right here. And so I could say that this is the cubic root of negative 1 times 2 times 2. Notice this equals 2, this equals 2, and this is still being cube rooted right there, which becomes 4 cubic roots of negative 1. But what is the cubic root of negative 1? The cubic root of negative 1, think about it, we could say negative 1 times negative 1 times negative 1. That's positive 1 times negative 1 is negative 1. So negative 1 cubed equals negative 1. Therefore, the cubic root of negative 1 is still negative 1. So this is the same thing as saying 4 times negative 1, which is negative 4. So our cubic root of negative 64 is negative 4. Try these out. These we're moving into more of the abstract with our variables here. So for here, if we were to factor this out, it's x times x. I've got a pair of x's here, so the square root of x squared is x. For here, for x to the 6, remember this breaks up into x cubed times x cubed. Because remember, if I multiply these, you add the exponents and get x to the 6. And then this breaks up into, I'm just going to do it like this, it breaks up into x times x times x. And same thing for this one, x times x times x. We are looking for groups of 3. So I've got one group of 3 right here, and another group of 3 right there. So the cubic root of x to the 6 is the same thing as x times x, which is x squared. And this should make sense if you were to cube x squared. Let's write that out. X squared to the third power, it should give you x to the 6. So you write out x squared 3 times, and you multiply. When you multiply them, you add the exponents, you get x to the 6. Try this one out. The square root of x squared y squared. This factors out into x squared times y squared. This factors into x times x and y times y. So you're looking for pairs since it's the square root. So there's one pair of x's and one pairs of y's. And so it becomes just xy. So when you have these now numbers or coefficients mixed in with the variables, just take each one separately here. We've got 28, and we're going to factor it out into 7 times 4, and 4 factors to 2 times 2. You have x cubed, which factors into x, x, x. You have y cubed, which factors into y, y, y. Since we're taking the square root, we're going to find pairs. So I've got a pair of 2's, so I pull out 1, 2. I've got a pair of x's right here, I pull out 1x. I've got a pair of y's right here, so I write down 1y. And then what's left over, a 7 times an x times a y, goes back underneath the radical. So it's still going to be square rooted, the 7, the x, and the y. And so that's my answer there. Pause the video and try out the next one here. So we have 2 times 100, 4 times 25, 5 and 5, 2 and 2. M to the 4th factors out into m, 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 and then y just stays like it is there. So I'm looking for pairs because I'm just doing the square root. I've got a pair of 2's, a pair of 5's, so I write those down. I've got a pair of m's and another pair of m's. And then what is left over? Left over, I have a 2 and a y. So that gets multiplied and gets put back underneath the radical. So 2 times 5 is 10. M times m is m squared. And then I'm going to take the square root of 2y. So kind of summing up some of this stuff and adding a few new things in here. These are your basic properties to radicals. So at some point you've seen this in Algebra 1 text. I just want to remind you of them and talk about them some. If you take the nth root of something raised to the nth power, you just get that base there. So they're just kind of inversing one another. If you take the nth root of a times b, you can rewrite that as the nth root of a times the nth root of b. Like if you had the cubic root of 5x, that's the same thing as the cubic root of 5 times the cubic root of x, if you need to there. Likewise over here, if you're taking the nth root of a fraction, you can break that fraction up, and sometimes that's helpful. So if I was taking the square root of 16 over x squared, I can rewrite this as the square root of 16 over the square root of x squared and simplify from there. And the other property here is being able to write a radical as an exponent can be very helpful. We'll see some examples of this here in a moment. But basically it's saying if we take like the 4th root of x cubed, I can rewrite this as x to the 3/4. So when we have an exponent that's a fraction, we're really dealing with a radical. So let's try out some other examples here using these properties. If I want to take the square root of 20x squared times the square root of 20x, how can I rewrite this? Well, since it's both to the same root, it's not like there's a 3 here and a 4 here, they're both 2's, I can say this is the same thing as the square root of 20 times 20 times x squared times x. I'm just kind of lining these up the way I want to multiply them. And so you could say that's the same thing as 400 times x cubed. Now if you actually did want to solve the rest of this problem, you got to kind of work backwards again and say, well, that's the same thing as 20 times 20. And 20 is the same thing as 4 times 5. So you got 2 of those. 4 will break up into 2, 2. So you end up with 2 times 2 times 5. And then another 2 times 2 times 5. And x breaks up into x, x, x. Since we're taking the square root, we're going to look for pairs. So I got a pair of 2's here. Write down 1, 2. Got another pair of 2's. Write down another one. I've got this pair of 5's right here. And then I have a pair of x's. The only thing left over is this 1x by itself. So it goes back underneath the radical. And then simplifying this, we get 2 times 2, which is 4. 4 times 5 is 20. So you end up with 20x times the square root of x. Now at this point, some of you may be saying you're doing way too much work here. I see an easier way, and there is an easier way. You could look at this right here as the square root of 400 times the square root of x cubed. And if you break up the square root of 400 into square root of 20 times the square root of 20, that's going to give you 20 right there. Or you could say, hey, I know the square root of 400 is just 20. And so that saves you a lot of factoring there. And then just break up the x cubed into that, pull out 1x, and you get 20x times the square root of x there still. So it saves you all this work over here if you recognize the square root of 400 to be equal to 20, or if you just realize that when you take square root of 20 times the square root of 20, you get 20. All right, some practice with rewriting these in exponent forms. Sometimes I get students get confused. They can't remember, is this x to the 3/4 or is it x to the 4/3? So what I like to tell students to go back and refer to, because we don't see the fourth root of something cubed that often, but what we do see a lot of is the square root of numbers. So if you remember that the square root of x is equal to x raised to the 1/2 power, then that should help you figure out which one is correct up here written in green. So for instance, we know that a 2 is hiding right there and a 1 is hiding right there. So it kind of tells you which part goes in the numerator and which part goes in the denominator. So right here, the 3, just like the 1 right here in the numerator, the 3 must go in the numerator here and the 4 in the denominator there. And you're saying, well, what if I don't remember it's 1/2? I can't remember what, maybe it's something else. If you can remember that this is x to the first and this is a 2, let's say you got it wrong. Would it be x to the 2 over 1? Well, x to the 2 over 1 is x squared. So how can the square root of a number equal that number squared? It doesn't really work out that way. So using this example, if you're writing this out on a paper, you're doing a math problem, you can't remember the fourth root of x cubed, is that to the 3/4 or the 4/3? Somewhere over on scrap paper, write out square root of x and rewrite it as exponent form, and it will kind of show you which numbers go in the numerator and which one goes in the denominator. So for this case, this would be wrong. We want this one right here. Same thing right here. We know that this is a 2, and so this is going to be y raised to the power of 5 over 2. Try this one out. These are just some problems to kind of finish off this lesson to get you some practice. So simplify that as much as you can. So for this one, I just kind of pay attention to the numbers first, and then I'll look at the exponents, the variables next. So 36 and 42 both have a 6 in common. So dividing them both by 6, I get 6 over 7. And then x cubed over x squared, 3 minus 2 gives me 1, so I end up with an x in the top. But don't forget you had a negative out front, so this answer is going to be a negative 6 over 7 times x. You could also write the problem like this, or the answer like this, negative 6/7 with an x on the side right there. This one, I notice that I've got 15 over 30. That they're both numbers divisible by 15. So 15 divided by 15 is 1. 30 divided by 15 is 2. And then you can rewrite, if it helps you can look at it like this, n over n cubed. These n's divide out and you end up with n squared in the bottom. Now, another way you could look at it is saying n to the first over n cubed, and subtracting them you get n to the negative 2, and if you write it as a fraction, remember the exponent's negative, it drops to the bottom and becomes n squared. So either way you want to look at it, this right here is your answer. Now you cannot write this one like this. This would be incorrect because this is saying n squared over 1, which puts the n squared in the numerator. So if it's in the denominator, it stays down there. It can't be kicked off to the side like it could have right here. Notice if I put the x over 1 and multiply, I get the answer up there. All right, try this one out. So for this one, oops, I'm going to try to move this off to the side so I have a little more room to work. I'm going to use that property where I can break this up some to the square root of 16x squared up top and the square root of 40xy cubed on the bottom. And that will allow me to cancel some things hopefully here in a moment. So the square root of 16x squared is the same thing as the square root of 16 times the square root of x squared. And then on the bottom I can rewrite this as the square root of 40 times the square root of x times the square root of y cubed, if I want to write it out like that. The square root of 16 I know is 4. And the square root of x squared is x. And then square root of x, I'm not going to be able to do anything with that, but I know that this is y times y times y, so you can pull out a y right here. And then let's break up 40 into 8 times 5. 8 breaks up into 4 times 2, and then you get 2 times 2. And so I've got a bunch of emails coming in apparently. Right here I've got a pair of 2s, so I'm going to pull out that 2 with the y. And all of this leaves me with 2, 5, x, and this y left over. That's what's going underneath the radical again. So 2 times 5 is 10 times x times y, so I end up with 10xy under the radical. And so this is what the denominator simplifies to. 2 times y times the square root of 10xy. And I notice I got a 4 over 2. This is my fraction with the radicals simplified, but now I can simplify the fraction. So 4 divided by 2 is just 2. So 2x over y times 10xy is my answer there. Let's try out the next one. So this one, we can't really FOIL this, but I want you to practice that distributive property. So we're going to draw swoopties going to each one. I'm going to first multiply everything by m. And that gives me m cubed n, that's m times m squared n, plus 2m squared, that's multiplying the m's there, minus 3m, and then multiply everything by 4. So I get plus 4m squared n plus 8m minus 12. And now I'm going to combine my like terms. I've got an m squared here, 4mn squared. So because it's not just m squared by itself, I can't combine those two. So I don't see any other m squareds, so nothing I can combine there. I don't see any other m cubed n's, or just, well actually I do have an m by itself, don't I? I got those two. So combining those I get 5m. Everything else though can't be combined, so just write out the rest of it. So those are done. 4m squared n minus 12, 2m squared, and m cubed n. It seems a little lengthy, but there wasn't much that combined there for me in the end. Try out this one. Now, this one, be careful because we can't always just cancel things because you see x's in the tops and the bottoms. These plus symbols give us issues. Like if this were x plus 2 over x, you can't cancel out the x's because 2 is also being divided by x. So you got to make sure you divide 2 by x as well. Remember that when we add fractions, we got to have the denominators the same, and then we can add the numerators. So for here, we could actually divide this fraction up. Not divide, may be a bad word, split it up, so that this is the same thing as x over x plus 2 over x. Now notice, if I gave you this problem and said, add that fraction, you say, okay, good, the denominator is the same, and I just add the numerators and I get this. So I can't just cancel this out and say it's equal to 2 because it doesn't. You could put a value in for x like 5. And notice that this does not equal 2, it equals 7 divided by 5. So over here, actually before we get over there, let's look and see what would make this work. If I had x plus 2x over x, then I could say that the x right here would cancel. Well, it wouldn't cancel, it'd equal 1. And the x right here would cancel, and I'd get 2, and this would equal 3 total. So if each term has that same variable in it, then you can divide it out. So for right here, you can do a couple of things, a couple of ways to show this. One, you could divide up the fraction. So let's clear some space here and divide up the fraction. This can be rewritten as x cubed times y squared over x plus x squared times y over x plus x over x. And then simplify. So you get x squared y plus xy plus 1. And there's your answer. That's one way you can do it. Another way you can do it is factor out an x in the top. Now we haven't really talked much about factoring, but as far as this step goes, it's kind of like the reverse of distribution. So you notice that each one of these have an x in common. So if I write down an x and then divide each one out by x. So this piece divided by x is x squared y squared, plus this piece divided by x gives you xy, plus this piece divided by x gives you 1. You can say that my numerator right here is the same thing as this numerator. Notice if you drew your swoopties and distributed the x, you would get this circled up here. And now from this step we can say these two x's can be divided because there's not an addition sign between this, there's a multiplication sign. And so dividing those out, this becomes your answer, which is what you see right here. Try that one out. So this is the same problem that we had right here, except for now I'm dividing by y. And so the issue we get right here is that this last term does not divide by y. So the only way we can really, it's not really simplifying it more, but if you really want to divide out that y on some of it, you could split this up and to say x cubed y squared over y, x squared y over y, it's a plus sign in between, and then plus x over y. And so this would simplify to x cubed y, and then this would be just x squared, and then we'd be adding x over y. I'm not saying that, I wouldn't really consider this a more simplified version of it. It's just a different way you can write it if you need it to. The algebra there is correct. So let's look at the next one. Now this one is the same thing as before, except for now we got an x times a y in the bottom. And so everything that we divide out here has to have some type of x being multiplied by a y. And so looking at this, I'm just going to look through each one and divide each one by xy. So x cubed divided by x is x squared, y squared divided by y is y, plus x squared divided by x is x, y divided by y is 1. And then xy divided by xy is 1. So that's what it simplifies to. This one, once again, it's actually probably simple after seeing those last few examples. You could do it a couple different ways. You could divide each term by 3 and get x plus 2. Or you could say on the top right here, let's factor out a 3. So if you factor out a 3, you get x plus, not x plus 6, but x plus 2. And it's all over 3. The 3's will divide out to 1, and you get x plus 2 again there. All right, well, I hope that quick review there, I know we went through a lot of different topics there, will help you out with the homework tonight. I don't want to go into too much depth if all of you remember it, but at the same time, if you went through that hour there of watching that video and you're struggling, contact me. We'll set up a time and go through some more examples and make sure you're caught up to speed with everything. All right, thanks for working hard, thanks for doing your best in this class, and I hope you're having a wonderful day as you do this.